Okay, so quick recap on the prior knowledge and skills from the last lesson. The last lesson that we had was actually the required practical lesson. So we were looking at changing concentration and looking at how that affected the rate of reaction. There was also quite a lot of graph drawing stuff in that one as well. Please do go back and have a look at that, particularly look at the videos for the actual practicals themselves, and also have a listen to how to answer the exam questions. Right, so the knowledge and skills we're going to be looking at in this lesson is as follows. You'll notice that actually we're looking at C8.6 and 8.7. Now that might sound like a lot, but there's in fact quite a lot of little practicals in this stuff, so it's not actually a huge amount of new knowledge and skills. So we're going to be looking at the fact that in some chemical reactions you can get the original reactants back again. We're going to be looking at the fact that they're called reversible reactions and how they can be represented. We're going to be looking at the fact that you can change the direction of a reversible reaction by altering the conditions. We're going to be looking at energy in these reactions and the fact that if it's exo in one direction, it's endo in the other, and the fact that that amount of energy is going to be the same every time. Right, so this particular lesson, C8.6, is all about something called a reversible reaction. Now, if you want a simple definition, you can probably guess from the name, but a reversible reaction is a chemical reaction in which the products, so that's the things at the end of the reaction, can reform the reactant. So if you like, it will be reversed. This symbol here, the double-headed arrow, well, it's not really a double-headed arrow, but the two half arrows going in each direction, is the symbol that is actually used for a reversible reaction. Okay. Now, to be honest, this is a pretty simple lesson. It's a kind of base level lesson for where we're going next. All right. So the main thing we're going to take out of this is this new little symbol here, and it's most likely you're just going to get asked about some of the examples that are going to be appearing on the next few slides. Okay, so this is the first example. This one is mentioned in the specification, and that is heating something called ammonium chloride. So if you have a little look at the equation here, the ammonium chloride, when we heat it up, it's going to decompose or break up into ammonia and hydrogen chloride. So these are the chemical formula for these particular chemicals. Ammonium chloride is a solid, and that is the white solid you can see in the bottom of this picture here. And when you heat it up, you form ammonia, which you might know is a gas, NH3, and hydrogen chloride, which is also a gas. Now notice this is hydrogen chloride, not hydrochloric acid. If it was hydrochloric acid, it would have an AQ here because acids only show their acidic properties when they are dissolved in water. So these two things are both colourless gases. So when we begin to heat the ammonium chloride, you will notice basically it doesn't look like there's anything directly above the white solid. That's because at that point forward reaction is occurring and you've formed ammonia gas and hydrogen chloride gas, which you can't see. Now this particular process, you're heating it, so you are providing energy, so therefore it is an endothermic process. You are putting energy in, so you're providing energy here. Now further up the tube it begins to cool down, so as you get further up the tube what happens is the reverse reaction starts to happen. Now you can probably guess if the forward process is endothermic, the reverse is exothermic. So at this point here, the ammonia and the hydrogen chloride are recombining and reforming this ammonium chloride solid. So this white stuff you can see here is the ammonium chloride solid that has been reformed. You've got a little bit of cotton wool in the top here just to stop any of the kind of fine powder coming out, and also of course it's not a bung because otherwise you blow it up. Okay, so example number 2 is something called cobalt chloride. It says cobalt chloride paper because paper is commonly soaked in cobalt chloride and used in chemistry labs to test for water, and we'll look at how we could do that in a second. So the chemical we're using is something called anhydrous cobalt chloride. The word anhydrous means without water, and that's this lovely blue colour. So this little strip of paper down here has been soaked in anhydrous cobalt chloride, hence it's blue. Now, where the pipette is adding a small amount of water, you can see that it has turned from blue to pink. And that pink colour is due to the hydrated cobalt chloride, which means hydrated means with water. Now, if you have a little look at the chemical formula, there's something here that looks a little bit probably unfamiliar. You've got a little dot and then the 6 waters. Essentially what that means is that the cobalt chloride has got 6 water molecules surrounding 1 cobalt chloride, and those 6 water molecules kind of form like a cage around the outside. And because for every one of those cobalt chlorides you get 6 waters, the ratio is the same every time, and because the ratio is the same every time, you can write it as a chemical formula. So essentially we're saying for 1 cobalt chloride there will always be 6 water molecules around the outside. So that's what that's about there. Now, if you actually, again, have a look at this reaction, that's obviously the forward process, adding the water to get the pink colour. But it says here it's reversible. So if it's reversible, that of course means that somehow we can go from the pink back to the blue. Now, this process, you might be able to guess how you can do it. So if you are adding water to go this way, you need to somehow remove the water to go the other way. And the easiest way to remove the water is just to heat it. So if you gently heat this, obviously not heat it directly with a Bunsen because it will burn, but if you gently heat it or dry it out in a desiccator, then a desiccator is basically a device that helps remove water. It's got little crystals in the bottom, a bit like the ones that you get in like silica gel packets in like shoe boxes and things to keep them dry. And that will help to remove the water, and it will go back to the blue colour. So that's example 2. Okay, example 3, heating hydrated copper sulfate. Okay, right, so hydrated, we met this word just now. Hydrated means with water, so it's copper sulfate with water, which is this lovely blue colour. It's this stuff down here in the bottom left. And if you heat it, you get anhydrous copper sulfate. Again, a word we met just now, and you will remember that anhydrous means without water. So this is a very similar reaction to the previous slide. Now, if you have a little look at the chemical formulae, you will notice again similarities. The anhydrous on the right hand side here, right, is white. Now I know that picture looks still a little bit blue, but that's probably because there's a little bit of the hydrated still in there, right? But anhydrous is white, obviously water we know, and then the hydrated one, just like before, we've got the 5 water molecules in the cage around the outside. Just so that if you are interested, the technical term for those water molecules is water of crystallization, because those waters basically form copper sulfate crystals. Right, so how does this work then? Well, if you heat up the blue copper sulfate, right, you will begin to see it turn white, unsurprisingly. You might also see tiny little bits of water vapor appearing as the water is driven off. Now, once again, because you are heating it, you are providing energy. So if you're putting energy in, this is an endothermic process. So you get your white anhydrous copper sulfate. Now, if we want to reverse the process, then of course what you've got to do is take your white copper sulfate, your anhydrous stuff, and add some water to it. Now, if you add a couple of drops of water, then in fact, of course, when that happens, that should be an exothermic process. Now, in fact, this particular experiment, right, it really is quite exothermic. So the heat you get from just adding a couple of drops of water, right, you really can feel the outside of that test tube getting very, very hot. Now, this just leads on to one of the other points that are in the specification statements you're supposed to know. So if you could measure the amount of energy released in that exothermic reaction when you added the water, if, for example, it was, I don't know, 500 kilojoules, then that would be exactly the same amount of energy as has been provided to go the other way, right, to turn it into the anhydrous copper sulfate. So the point is, the energy absorbed in the forward direction of this would be identical to the energy released in the reverse direction. And very occasionally they do ask you about that in exam questions. Okay, final example is indicators. So all indicators work in a very similar way. You are probably most familiar with universal indicator. Universal indicator is slightly confusing because it's a large range of colors. And the reason it's a range of colors is because it's actually a mixture of lots of different indicators. Indicators are substances that just change from one color to another at a specific pH. So the one we're going to have a quick look at here is something called litmus, which you might remember from way back in, I don't know, year 7, maybe even year 6, right? And litmus will go pink in acids and blue in alkalis. However, all indicators work under the same principle as this one. Right, so blue litmus, if you then add acid to it, it changes colour to form red litmus. And here's the reversible reaction to that happening. Now, this is where this one's slightly confusing. Litmus itself, the chemical structure, I'll put it up in a second, is really quite complex. So we are going to basically abbreviate it to lit, right, and lit, right? Because indicators will change colour with any acid, you should know from your previous unit C5 that all acids contain this here, which you should recognise as a hydrogen ion. And again, you might remember just from previous in this PowerPoint that acids only show their acidic properties when they are aqueous or dissolved in water. So if you add any hydrogen ion to this blue litmus, you will notice my blue litmus has got a little negative charge there. That's because it's a negative ion, right? Then what will happen is they will combine and you will just get the hydrogen bonded to the litmus. And when it does that, it actually changes the colour of that compound and forms red litmus. So for those people who'd like to know, these are the actual structures. They look pretty complex. These weird hexagons are a bit funny, but essentially every time there is a corner, that is a carbon atom. All right, that's a double bond, that's a single bond, right? And each carbon atom is always assumed to have 4 bonds. So the carbon there would have 2 going to an oxygen upwards, 1 going here, 1 going here. This carbon atom here would have 2 going downwards, 1 to the top left. But actually, if it's supposed to have 4 bonds, what happens to the other one? Well, you assume that if it's got extra bonds, then it will be bonded to a hydrogen. So there'd be a hydrogen there. Do not worry too much about this, all right? It's essentially just to try and show you that the structure is quite complex. That's why we just abbreviate it here. And you will notice there's a negative charge in this oxygen here. When you put acid with it, what happens? Well, that hydrogen ion bonds here, and you get this compound, which is almost the same, but subtly different here. And just that subtle change changes the colour. So you get red litmus over here. Right, again, the details of this, you really don't need to know too much other than the fact that it's a reversible process. So therefore, to get back, go back the other way, right, basically, if you had acid this way, you would add alkali to send it back the other way. Okay, so this is just a quick checking understanding slide. So see if you can have a go at these questions down here. So name the type of reaction shown by that lovely sign there. I'm sure you know that. When the student added water to the anhydrous cobalt chloride, what happened? All right, so hopefully you should be able to answer that, or if not, have a quick look back and find out. Last one's a suggest question. So remember, suggest questions are ones that aren't straight off the specification, but they're where you have to use your understanding to try and work something out. So it says, suggest why the jar containing the unused cobalt chloride papers must be kept closed. Right, so have a go at those, and then the answers are on the next slide. Okay, so here's your answer slide. I'm sure you all know that that symbol is the reversible reaction symbol. When you add the water to the anhydrous cobalt chloride, it changed from blue to pink. Are you supposed to know that colour change? Well, it is mentioned in the specification, this particular reaction, so there is a chance that they might ask that. And then suggest, well, you keep your cobalt chloride papers in a sealed jar because that will stop any moisture from the air or any water from the air reacting with your cobalt chloride paper. Okay, and finally, let's have a quick look at some of these bits and pieces here. So in some chemical reactions, the products of the reaction can react to produce the original reactants. Okay, that is a fact. And these reactions are called reversible reactions and are represented like this. Hopefully you're okay with these things. Then point number 3, the direction of a reversible reaction can be changed by changing the conditions. Right, so what we mean by that is if you have to heat it in one direction, you cool it in the other way. If you had to add acid in one way, you'd add alkali the other way. If you had to add water in one direction, you would remove water the other way. So essentially, if you change the conditions of that reaction, you'll get either one side or the other. If a reversible reactant is exothermic in one direction, it will be endothermic in the opposite. Hopefully you've picked that up throughout the lesson. And finally, the same amount of energy is transferred in each case. So I did mention this earlier on. So if you had 100 kilojoules of energy being absorbed in a forward reaction, you would have exactly 100 kilojoules of energy being released in a reverse reaction.